Volume of revolution. If we take the area under the curve y equals f of x and rotate it about the x-axis one complete revolution, we would get a solid. And I just want to look at the construction of this solid before we do anything else. So I'm just going to use autograph here. And what we're going to do is first of all find area. And let's do that fairly big so we can see it well, from 0 to 2, using 8 rectangles, and these rectangles fit under the curve, so they look like that. So we're just approximating the area. We can see there's bits left out, but this gives an idea of what we're going to do. We're going to rotate this completely around the x-axis here. So to do that, I'm just going to select this area and then say find volume, and we'll just OK that, and it will start to do it, and we can see that it's starting to rotate around. And so what we get is the volume approximated by some cylinders, and we can see those cylinders reasonably clearly if we move the graph around like so. Now, one thing we could do to show how this fills the volume better is if we just change the area settings here, and instead of having 8 rectangles, let's do it with, say, 24. We can see that it'll fill much better. So we can see these rotating around, and we can see that it gives a much better impression of that area now. So now that we've seen that, we should have a better understanding when we look at this. So what we're talking about is an area here being rotated around, and we know that that's going to form a series of disks. To find the volume of the solid, we could imagine dividing it up into many small segments, each with a thickness of delta x. So these were the disks that we saw before. Each of the segments is approximately a cylinder. The ones that I used on autograph were cylinders because we started with rectangles. So this is the situation that we saw. The volume of each of the segments, approximating as a cylinder, would be pi y squared dx. So that's the area at the end multiplied by the thickness. The total volume would be the sum of all the segments. This would become more accurate as the width of each segment approaches 0. We saw when I used 24 divisions how much better it was than when we used 8. With the usual calculus argument, we want an infinite sum of infinitesimally thin segments. So the volume would be the limit as delta x tends to 0 between a and b of pi y squared delta x, and that's the integral from x is a to x is b of pi y squared dx. Remember, pi is a constant, so you can slide it outside of this integral. If we rotate around the y-axis, a similar argument gives us that the volume is the integral from y is a to y is b of pi x squared dy.